So, we saw what a first order differential equation, we saw different types of first order differential equation, and we said that the general strategy of solving differential equations is to separate the variables. Okay. Now we look at cases where you cannot separate the variables, then what can you do? And today's topic will be exact differentials, which will be the way of solving differential equations where you cannot easily separate the variables. Okay. So, before talking about exact differentials, I just want to mention one thing, that sometimes you have sometimes. So, we can use a change of variables to separate equation. So, your differential equation might be converted to separable form by a change of variables. So, an example of that is, suppose you have a differential equation. So, example, suppose you have x y prime equal to x plus y. Okay. Now, you can see this, you cannot try to separate. So, you cannot separate this, not separable. Okay. However, let us say u equal to y by x. Okay. So, suppose you set u equal to y by x, set u equal to y by x. So, you are changing a variables from your dependent variable from y to u. Okay. So, suppose you set u equal to y by x, then you can immediately write y equal to ux, and you can write dy by dx is equal to which is also denoted by y prime. This I can write it as u prime x plus u. Okay. So, so how does this help you? Okay. So, you just, if you just replace y by u prime x plus u, or if you replace y prime by u prime x plus u, okay, then what you will get is u prime x square plus u x equal to x plus y is u x. Okay. And what you can see is that immediately one x will cancel. Okay. So, you can cancel one x. So, what you get is u prime x plus u is equal to 1 plus u. Okay. And again also a u will cancel. So, this you can write implies u prime x equal to 1 or du by dx equal to 1 by x, and you can solve this and you will get u is equal to log of x plus constant, and you can go back and you can write y is equal to ux. So, that is y equal to x log x plus constant times x. So, that is this is the solution. So, you solve this equation which did not look separable initially by doing a change of variables. So, sometimes a change of variables can convert a differential equation into a separable form. Okay. Now, often you cannot separate differential equations. However, there is still something to say. So, in this case, in this particular case, we just looked at the differential equation and we chose this transformation of variables. But suppose you are asked, how do you know whether a differential equation will have such a transformation of variables? How do you know that a differential equation can be converted to separable form? Okay. So, to answer that question, we will address the issue of exact and inexact differentials. And here what we will do is we will rewrite the differential equation in a slightly different form. So, we will rewrite the differential equation in the form m of x y dx plus n of x y dy equal to 0. So, I just rewrote the differential equation, not every differential equation can be written in this form, but let us assume that you can write the differential equation in this form. So, notice that this basically implies dy by dx equal to minus m of x y divided by n of x y. So, it is an explicit differential equation, whatever your dy by dx is you can. So, if you can write an expression for dy by dx, then you can write it in this form. Okay. So, this is the differential equation, and now you know that when we studied vectors, okay, and we studied gradient of a vector, we studied potential theory. So, when we studied potential theory, we said that force can be expressed as a gradient of a potential if the various components satisfy some relation, and exactly the same idea can be used here. So, can we write du is equal to m of x y dx plus n of x y dy. So, is there some u, okay, some u which is a function of x y such that du can be written in this form. So, can we write this? And the answer is, if you can, if yes, then you say m dx plus n dy is exact, else m dx plus n dy is inexact. Okay. So, this is the basic idea of exact and inexact differentials, that if you have this differential equation and you want to write this whole differential on the left as du. Okay. So, that is what we want to do, and we want to ask, can we do it? If you can do it, then you say that it is an exact differential. If you cannot do it, you say it is an inexact differential. So, what is the condition for exact and inexact? Condition for m of x y dx plus n of x y dy to be an exact differential. So, what is the condition? And I will write the condition and then it will become clear why that is the condition. So, the condition is partial derivative of m of x y with respect to y. So, the partial derivative of y means you keep x fixed. Okay. So, this should be equal to partial derivative of n of x y with respect to x. Again you keep y fixed, and you have already seen such conditions when we did potential theory, or when you do thermodynamics you see such conditions. Okay. So, this is a condition for m dx plus n dy to be an exact differential, and it is very easy to see why this condition helps to make this an exact differential. Okay. So, to understand that, what we want to do is, if du equal to m x y dx plus n of x y dy is exact, then we have du is equal to dou u by dou x dx plus dou u by dou y dy. Okay. So, this implies dou u by dou x is equal to m of x y and dou u by dou y is equal to n of x y. Okay. So, if this were an exact differential, then this is what it really implies about m and n. Okay. So, now you can see the condition. So, therefore, the condition, your condition, this condition basically implies the following. So, if you replace m by dou u by dou x, then you have dou by dou y of dou u by dou x. So, that is dou square. So I will call this condition 1, So, condition 1 implies dou square u by dou x dou y is equal to dou square u by dou y dou x. Okay. And if u is a smooth function of x y, then this is satisfied. Okay. So, therefore, you can see the connection why we insisted that this should be the condition for exact differential. Okay. So, now so what does this mean? This means that you can take any differential equation, you can check is it exact, is it not. Okay. So, and that is a very nice thing, you know, where so you can easily check that it is exact or not. Now, if it is exact, if your differential equation is exact, okay, then what happens? If dE is exact, then you have these two conditions, you have dou u by dou x equal to m. So, u then du equal to 0 implies u of x y equal to constant. This is your implicit solution. So, you can solve the differential equation very easily if it is exact. Okay. So, let us take an example. Okay. I will not discuss the change of variables yet. Okay. So, let us take an example. Okay. So, I will not be discussing this, let me just take an example of exact differential. So, suppose you have dy by dx is equal to minus 2xy square plus y plus x cube divided by 2x square y plus x plus y. Okay. So, what I will do is I will rewrite this as so this times dx I will bring it to the left. So, I have 2xy square plus y plus x cube dx plus 2x square y plus x plus y dy equal to 0. So, this is my, and you can verify. So, your term dou m by dou y is equal to 4 x y plus 1, dou n by dou x is equal to 4 x y plus 1. So, clearly it is an exact differential. So, this is an exact differential. Okay. Now, how do you solve this exact differential equation? So, you know that this quantity is nothing but dou u by dou x. Okay. So, you say that dou u by dou x is equal to 2xy square plus y plus x cube. You can use either of them. You can use either dou u by dou x or you can use dou u by dou y. Okay. And now, if I integrate the right hand side with respect to x, remember when you do dou u by dou x, you are keeping y fixed. So, you are in, so now this integration is very straightforward. So, you will immediately say that u is equal to x square y square plus x y plus x raised to 4 divided by 4 plus constant. And remember the solution of the differential equation, now you have to be a little careful. So, this constant of integration, so constant depends on y. Okay. So, I should write c of y, okay, because I had a partial derivative with respect to x. So, any function of y, if I take the derivative with respect to x, it will go to 0. So, if I have this, you can verify that a derivative with respect to x will give me exactly the above equation. Okay. So, this is a form of u. Okay. Now, further you know that dou u by dou y is equal to 2x square y plus x plus y, and this is from the differential equation from here. Okay. So, what can you say? So, therefore, what you will say, if I take dou u by dou y here, then I will get 2 x square y plus x plus dou c by dou y. Okay. And what you immediately get is that dou c by now these two will cancel each other. So, I will just cancel this, similarly x will cancel. So, what you will be left with, this implies dou c by dou y is equal to y, or c is equal to y square by 2. Okay. So, by doing this we got this c of y, and so I can write the total u. So, my solution of differential equation is u equal to constant equal to x square y square plus x y plus x 4 by 4 plus y square by 2. Okay. So, this is a constant. So, we solve this differential equation by this method of exact differentials. Okay. So, I think this use of exact differentials to solve differential equations is actually a very powerful method. Okay. And I will just write, I will just emphasize the steps again. So, in the solution by exact differentials, so first we had m dx plus n dy equal to 0. So, we took advantage of the fact that m, so we set this equal to du, okay, and what we wanted to do is to find this u is a function of x y, okay, just like m and n. So, what you said is that dou u by dou x equal to m, okay, and so I can write u as integral m dx plus some function, I will just call it g of y, okay. Then you had dou u by dou y equal to n. So, therefore, I can write dou u by dou y, I can write as dou by dou y of integral m dx plus dou g by dou y equal to n, okay. And this allowed us to solve for, this gives a differential equation in g, okay. So, you can solve for g. For g of y, okay. And once you have solved for g of y, then you have your solution of the form u equal to integral m dx plus g of y equal to constant. So, this is my solution of this differential equation. Okay. So, we see how you can use the idea of exact differentials to actually solve a differential equation that otherwise if you did not use this idea, then this differential equation actually looks very complicated. So, if you just take this differential equation, okay, then it does not look like you can separate x and y, okay. It looks like x and y are very, it looks like a very complicated equation where you cannot separate x and y, okay. But by going through this idea of exact and inexact differentials, okay, we actually related the numerator and the denominator to derivatives of some function which is the solution, okay. And the only reason we could do this was because you had this equation of this exact differential, that dou m by dou y was equal to dou n by dou x, okay. So, this is a very powerful method to solve first order differential equation, okay. And what it says is that even if you cannot separate the variables, you can still go ahead and solve first order differential equations. Now, what happens if m is not exact, okay. So, what happens, what if m dx plus n dy is not exact, okay, and that is dou m by dou y is not equal to dou n by dou x. What can you do in such a case? Okay. So, now there are two things to do. So, one is can we change variables? Okay. So, sometimes you are able to find some tricks where you suitably change variables and suddenly you get the solution. Okay. So, this is not always reliable. Okay. So, it might not be possible. So, you just have to see whether you can change variables and you can get to this. Okay. So, the other method that we will be discussing in the next lecture will be that of integrating factors. Okay. And this is the other trick that we will be using when you want to solve differential equations, first order differential equations. So, in the next class I will be talking about integrating factors and how you can use the idea of integrating factors to solve differential equations where you cannot use the ideas of exact differential. Okay. So, I will stop here for today now.